For over 3 decades, the Hubble Space Telescope has been humanity's eye into the vast unknown, capturing images that blend art and science in breathtaking clarity. Launched in 1990, Hubble has peered into the depths of space, revealing distant galaxies, star-forming nebulae, and the remnants of dying suns. Its mission was to serve as a window to the ancient past, capturing light that has traveled billions of years to reach us. From its perch in low Earth orbit, Hubble has mapped the cosmos with unparalleled precision, offering glimpses of the universe's grand architecture, spiral galaxies swirling in elegant arcs, nebulae glowing with ethereal light, and the faint whispers of the Big Bang's afterglow. Its images are not just scientific data, they are a testament to humanity's curiosity, a visual symphony of the cosmos that has inspired generations. Yet, in 2025, Hubble did something no one anticipated. Designed to observe slow, majestic processes unfolding over eons, it caught a fleeting moment that defied its purpose. A cosmic event so brief, so intense, and so unexpected that it reshaped our understanding of the universe. This is the story of that moment, a flash of ultraviolet light that flickered in the dark, challenging the boundaries of science, technology, and even philosophy. It's a tale of discovery, of a telescope past its prime, proving that the universe still holds secrets waiting to be uncovered. This is the story of Hubble's cosmic flash, a beacon that illuminated not just the sky, but the very nature of existence. In a routine observation of a distant galaxy, Hubble's sensors recorded something extraordinary, a burst of ultraviolet radiation, brighter and faster than anything in its 35-year archive. This wasn't a supernova whose light lingers for weeks, nor a quasar whose energy pulses over millennia. This was a transient event, a flare that surged into existence and vanished within seconds, defying every model of cosmic behavior. The galaxy, located billions of light years away, had been studied countless times before. It was considered quiet, an unremarkable patch of space with no active star formation or violent activity. Yet, in that fleeting moment, it became the stage for a cosmic mystery. The light's intensity was staggering, concentrated in the ultraviolet spectrum, a range Hubble was uniquely equipped to detect despite its aging instruments. Initial analysis suggested a glitch, perhaps a cosmic ray striking the telescope's detectors. But the data told a different story. The signal was coherent, structured, and unlike anything cataloged. It wasn't random noise, it was a deliberate pulse from the universe, as if the cosmos had blinked. The event's brevity, mere seconds, made it all the more astonishing. Hubble, built for long exposures capturing the slow dance of galaxies, had stumbled upon a phenomenon that demanded split-second precision. This wasn't just a discovery, it was a revelation that the universe is far more dynamic than we ever imagined. The scientific community erupted with theories, each more tantalizing than the last. Could this be the birth of a magnetar, a neutron star with a magnetic field so powerful it could outshine entire galaxies for a moment? Some proposed a fast blue optical transient, FBOT, a newly identified class of explosive events that blaze and fade in days. But even FBOTS didn't fully explain the data. The flare's ultraviolet intensity and abruptness suggested something entirely new, something that didn't fit within the known taxonomy of cosmic phenomena. Researchers began exploring exotic possibilities, the evaporation of a primordial black hole, a remnant of the Big Bang releasing its final energy in a brilliant burst, or perhaps a topological defect in spacetime, like a cosmic string snapping and releasing a flood of radiation. More speculative minds ventured further. Could this be a white hole, the theoretical opposite of a black hole, spewing matter and light before collapsing? Or was it a bridge event, a fleeting interaction between our universe and another, as predicted by some multiverse theories? These ideas, once confined to the fringes of theoretical physics, gained new legitimacy. The flare's spectral purity and rapid decay hinted at processes beyond stellar mechanics. Perhaps quantum-scale ruptures in the fabric of reality or interactions involving dark matter. Whatever it was, the event suggested that the universe is not just a place of slow, predictable evolution, but a stage for sudden, violent outbursts that vanish before we can fully grasp them. The discovery of Hubble's cosmic flash didn't merely add a new data point to the astronomical catalog, it triggered a seismic shift in the scientific paradigm governing how we observe and interpret the universe. For centuries, astronomy has been rooted in the assumption that the cosmos operates on grand, predictable timescales. Stars burning for millions of years, galaxies merging over billions, and the universe itself expanding in a slow, measurable cadence. The flare, however, introduced a new temporal dimension to this framework, one defined by immediacy and impermanence. This single event, lasting mere seconds, exposed a critical blind spot in our observational strategies. Our instruments, including Hubble, were designed to capture the eternal, not the ephemeral. Suddenly, the cosmos wasn't just a static tapestry to be studied over long exposures. It was a dynamic, pulsating entity, alive with events that demanded real-time detection. This shift spurred a global reevaluation of astronomical priorities, with institutions like NASA and the European Space Agency redirecting resources toward developing instruments capable of high-cadence observations. The flare became a catalyst for a new kind of science, one that embraced the unpredictability of the cosmos and sought to capture its fleeting moments. It challenged astronomers to rethink their assumptions about cosmic stability, suggesting that the universe's most profound secrets might not lie in its enduring structures, but in its sudden, brilliant interruptions. Hubble's accidental discovery forced astronomers to rethink their approach to the cosmos. For decades, telescopes were designed to capture the universe's grandeur through long exposures, stacking faint light from distant objects to reveal their secrets. But this flare exposed a blind spot. The universe is alive with rapid, transient events that slip through the cracks of traditional observation. Hubble's aging optics, never meant to catch such fleeting moments, had revealed a new layer of cosmic activity. The implications were profound. If a 35-year-old telescope could detect such an event, how many others had gone unnoticed? This realization sparked a revolution in observational strategy. Astronomers began combing through Hubble's vast archive, using machine learning to search for similar anomalies hidden in decades of data. These algorithms, trained to detect sudden changes in brightness rather than static patterns, uncovered hints of other flashes, faint, overlooked blips that had been dismissed as noise. The discovery suggested that the universe might be pulsing with these events, occurring dozens or even hundreds of times daily, invisible to most instruments because of their brevity. To catch them, a new generation of telescopes would be needed, not larger, but faster, capable of scanning the sky in real time for the smallest flickers of change. The cosmic flash detected by Hubble reverberated far beyond the realm of astronomy, igniting a cascade of interdisciplinary exploration that bridged physics, philosophy, and even computer science. The event's enigmatic nature, its refusal to fit neatly into existing models, drew the attention of quantum physicists, who saw in its spectral purity a potential signature of vacuum fluctuations or quantum entanglement manifesting on a cosmic scale. These theorists posited that the flare might represent a rare glimpse of the universe's underlying quantum structure, where the boundaries between matter, energy, and space-time blur. Meanwhile, philosophers seized on the discovery to question the nature of causality and emergence, debating whether such spontaneous events challenge the deterministic frameworks that have long underpinned scientific thought. In the realm of technology, the flare's detection spurred advancements in artificial intelligence as data scientists developed sophisticated algorithms to mine Hubble's archives for similar transients, pushing the boundaries of machine learning applications in real-time data analysis. This interdisciplinary convergence transformed the flare into a unifying puzzle, drawing experts from disparate fields into a shared quest to decode its origins. The event became a nexus for collaboration, fostering dialogues that transcended traditional academic silos and highlighted the interconnectedness of human knowledge in the face of cosmic mystery. It underscored a profound truth: a single moment in the universe could spark a renaissance of thought, uniting disciplines in a collective pursuit of understanding. The flare's implications extended beyond science, stirring philosophical and cultural ripples. If the universe is peppered with such brief, brilliant events, what does that mean for our understanding of reality? Philosophers pondered whether these flashes were glimpses of a more volatile cosmos, where causality itself might bend under extreme conditions. Could they be the fingerprints of exotic matter or quantum fluctuations manifesting on a cosmic scale? The absence of lingering traces, no gravitational waves, no neutrinos, no X-ray counterparts, suggested that these events might not follow the usual rules of cause and effect. They might be spontaneous, emerging from the void without precedent, challenging the very notion of a deterministic universe. In the public imagination, the flare became a symbol of mystery and possibility. Media outlets hailed it as the dawn of a new astronomical era, while artists and writers wove it into tales of cosmic signals and hidden civilizations. The idea that the universe could speak in fleeting bursts rather than steady signals prompted a reevaluation of the search for extraterrestrial intelligence. What if advanced civilizations used high-energy ultraviolet pulses for communication, deliberately briefed to avoid detection? Hubble's discovery suggested that our search for life might need to shift from seeking persistent signals to capturing ephemeral ones, recalibrating our tools and assumptions. The cosmic flash captured by Hubble transcended the confines of academic discourse, igniting a cultural phenomenon that resonated across the globe. In an era where humanity grapples with existential questions about its place in the universe, this fleeting burst of light became a powerful metaphor for hope, mystery, and the unknown. Social media platforms buzzed with discussions, from scientifically grounded analyses to imaginative theories about alien civilizations signaling their presence. Artists seized upon the flare's ephemeral beauty, creating works that depicted it as a cosmic firefly, a brief spark against the infinite dark. Musicians composed ambient tracks inspired by the event, blending ultraviolet frequencies into soundscapes that evoked the universe's hidden rhythms. In literature, the flare inspired a wave of speculative fiction, with authors imagining it as the final transmission of a long-lost civilization or the birth cry of a new form of cosmic consciousness. Documentaries and podcasts explored its implications, framing it as a moment when humanity glimpsed the universe's untamed heart. This cultural outpouring wasn't just about the science, it was about what the flare represented, a reminder that the cosmos is not a distant, abstract entity, but a living presence, capable of surprising us in ways that spark wonder and curiosity. Schools incorporated the discovery into curricula, encouraging students to explore the intersection of science and imagination. The flare became a shared moment of awe, uniting people across cultures in a collective gaze toward the stars, reminding us that even in our technologically advanced age, the universe can still evoke a childlike sense of wonder. The flare underscored Hubble's enduring value, a reminder that even outdated technology can yield groundbreaking discoveries when paired with curiosity and innovation. Launched in an era of analog dreams, Hubble has been upgraded over the years, but remains a relic by modern standards. Yet, its accidental glimpse into the vast universe proved that legacy instruments can still surprise us. Engineers scrambled to optimize Hubble's systems for shorter exposures, while data scientists re-examined its archives for hidden treasures. The telescope, nearing the end of its operational life, had become a beacon of persistence, proving that wonder doesn't fade with age. This event also galvanized plans for future observatories. Space agencies worldwide began discussing high-speed ultraviolet telescopes designed to monitor the sky continuously, acting as cosmic motion detectors. Prototypes for distributed sensor arrays, networks of small, low-cost telescopes, were proposed to catch transients across vast swaths of the sky. The James Webb Space Telescope, with its infrared focus, and the upcoming Nancy Grace Roman Space Telescope, designed for deep surveys, weren't built for this task. Hubble's unique sensitivity to ultraviolet light had given it an edge, highlighting the need for instruments that prioritize speed over depth. Hubble's cosmic flash not only reshaped scientific thought, but also sparked a technological renaissance in astronomical instrumentation, pushing engineers and scientists to reimagine how we observe the universe. The flare's detection exposed a critical gap in our observational arsenal: the lack of instruments designed for high-speed, multi-wavelength monitoring. In response, research teams worldwide accelerated efforts to develop next-generation telescopes optimized for transient events. Projects like the Ultraviolet Transient Astronomy Satellite, UltraSat, slated for launch in 2026, were fast-tracked, with designs refined to capture ultraviolet bursts with millisecond precision across wide fields of view. Meanwhile, innovative proposals emerged for global networks of ground-based telescopes equipped with ultra-fast sensors, capable of coordinating in real time to track anomalies across the sky. These systems would leverage artificial intelligence to instantly analyze data, triggering alerts to other observatories within seconds of a detection. The flare also prompted a re-evaluation of data storage and processing, as astronomers recognized the need to preserve raw, unfiltered data rather than compressed images that might discard subtle transients. This shift required significant upgrades to data infrastructure, with institutions investing in high-capacity servers and advanced algorithms to handle the deluge of information. The technological push extended beyond astronomy, influencing fields like machine learning and real-time computing, as the challenge of detecting cosmic flashes demanded innovations that could benefit industries from telecommunications to autonomous systems. Hubble's accidental discovery thus became a catalyst for a new era of technological creativity, proving that a single moment in the cosmos could drive advancements that ripple across human endeavor. The Hubble flare ignited a global collaborative spirit, uniting astronomers, engineers, and data scientists in a shared mission to unravel its mysteries. Observatories across the world, from the Atacama Large Millimeter Submillimeter Array in Chile to the Square Kilometer Array in Australia, began coordinating efforts to monitor the flare's coordinates for any residual activity, creating a global network of eyes on the sky. International research consortia formed overnight, pooling resources to cross-reference Hubble's data with archival observations from other telescopes, including the retired Spitzer Space Telescope and ground-based facilities like the Very Large Telescope. This collaborative push extended to citizen scientists, who joined the effort through online platforms analyzing raw Hubble images for subtle anomalies that automated systems might miss. Universities and research institutes launched open-access databases, sharing the flare's spectral data and light curves to encourage contributions from independent researchers and amateurs alike. This unprecedented cooperation transcended national boundaries, with space agencies from the United States, Europe, China, and India aligning their priorities to develop a unified strategy for transient astronomy. The flare became a rallying point, demonstrating that humanity's quest to understand the cosmos thrives on collective effort. It reminded the global scientific community that no single institution or nation can fully grasp the universe's secrets alone, fostering a spirit of unity that promises to shape the future of astronomical discovery for decades to come. Beyond the technical and scientific, the flare touched something deeper. It reminded humanity that the universe is not just a place of order and symmetry, but a realm of surprise and spontaneity. The cosmos, long viewed as a slow, majestic tapestry, revealed itself to be a living, breathing entity, pulsing with moments of brilliance that vanish as quickly as they appear. This discovery challenged our assumptions about time, motion, and existence itself. If reality can produce such events without warning, what else lies beyond our perception? Are we glimpsing the edges of a universe that defies our models, where the laws of physics stretch and bend in ways we can't yet comprehend? The flare also reignited a sense of awe. For astronomers, it was a call to look closer, to question the familiar, and to embrace the unknown. For the public, it was a reminder that the stars are not just distant points of light, but storytellers, whispering secrets in bursts too quick for us to catch unless we're ready. Hubble's moment of serendipity showed that discovery often comes not from meticulous planning, but from daring to look and being in the right place at the right time. The universe, it seems, rewards those who keep their eyes open, even when the odds seem stacked against them. As researchers continue to analyze the flare's data, the mystery deepens. Its coordinates have been reobserved, but no repeat event has emerged. Yet, the absence of a second flash doesn't diminish the first impact. It has already changed how we watch the sky, inspiring a shift from passive observation to active, real-time monitoring. Autonomous systems are being developed to trigger alerts across global observatories when anomalies appear, ensuring that no fleeting event goes unnoticed. The era of slow astronomy is giving way to a new paradigm, one that embraces the universe's unpredictability. The flare's legacy is not just in what it was, but in what it represents. A challenge to our assumptions, a spark of curiosity, and a reminder that the universe is vast, complex, and full of surprises. Hubble, in its twilight years, has given us a gift, a fleeting glimpse of a cosmos that is not just ancient and eternal, but vibrant and alive, flashing with moments of brilliance that demand our attention. As we build new tools and refine our questions, we carry forward the lesson of that cosmic blink. The universe is speaking, and we must learn to listen faster. The technical details of Hubble's detection are as remarkable as the event itself. The flare was captured by Hubble's Wide Field Camera 3, an instrument installed during its final servicing mission in 2009. Designed to capture ultraviolet and visible light, the camera was conducting a routine survey when it recorded the anomaly. The exposure, lasting just 1,000 seconds, was not optimized for rapid transients, making the detection even more extraordinary. The signal's light curve, a graph of brightness over time, showed a steep rise and an equally abrupt decline, unlike the gradual slopes of supernovae or the prolonged pulses of gamma-ray bursts. Spectral analysis revealed the flare's dominance in the ultraviolet range, with a peak wavelength suggesting temperatures exceeding 100,000 Kelvin. This ruled out many conventional sources, as few astrophysical phenomena can produce such intense, short-lived ultraviolet emissions. The host galaxy, cataloged as a quiescent elliptical galaxy, offered no clues. Its stars, mostly old and stable, lacked the conditions for explosive events like supernova or stellar mergers. This mismatch between the event and its environment deepened the mystery, prompting researchers to question whether the flare originated from an object or from space-time itself. To unravel the flare's origins, astronomers turned to multi-wavelength observations. The James Webb Space Telescope, with its infrared capabilities, was tasked with examining the same region for residual heat signatures. The Chandra X-ray Observatory searched for high-energy counterparts, while radio telescopes like the 500-meter Aperture Spherical Telescope, FAST in China, scanned for low-frequency echoes. Yet no other observatory detected the event, underscoring its fleeting nature and Hubble's unique timing. The lack of corroboration wasn't a setback. It highlighted the need for coordinated real-time observation networks. On Earth, data scientists deployed advanced algorithms to sift through Hubble's archives. These programs, trained on neural networks, identified subtle patterns in pixel brightness that human analysts might overlook. Early results suggested that similar transients might be hiding in past images, mistaken for cosmic rays or calibration errors. This archival treasure hunt has become a priority, with teams worldwide collaborating to reprocess decades of data. The goal is not just to find more flares, but to estimate their frequency and distribution, potentially rewriting our understanding of cosmic dynamics. The flare has accelerated plans for next-generation observatories. Concepts like the Ultraviolet Transient Astronomy Satellite, UltraSat, set to launch in 2026, aim to fill the gap Hubble exposed. UltraSat will monitor large swaths of the sky in ultraviolet with a cadence designed to catch events lasting seconds to minutes. Other proposals include arrays of small, low-cost telescopes networked to act as a global sky monitor, capturing transients across multiple wavelengths. These instruments will complement larger telescopes like Webb and Roman, creating a more comprehensive picture of the universe's fast-paced phenomena. The flare also highlighted the value of versatility in telescope design. Hubble's broad wavelength coverage, a feature of its 1980s engineering, allowed it to capture what newer, specialized instruments missed. This lesson is shaping future missions, with designers prioritizing flexibility to ensure that no corner of the electromagnetic spectrum or the temporal domain is overlooked. The flare has become a rallying cry for a new era of astronomy, one that embraces the unexpected and prepares for the ephemeral. Beyond science, the flare has captured the public's imagination. Social media platforms buzzed with speculation, from scientific discussions to fantastical theories about alien signals. Artists depicted the event as a cosmic lighthouse, a fleeting beacon in the dark. Writers crafted stories of civilizations using ultraviolet bursts to communicate across galaxies, their messages lost to us until now. These cultural responses reflect a universal human impulse to find meaning in the unknown, to see ourselves in the stars. Philosophically, the flare challenges our understanding of time and causality. If events can arise without precursors, what does that mean for our models of reality? Some theorists propose that the universe might be inherently unpredictable, with spontaneous events shaping its evolution in ways we can't yet predict. Others see the flare as evidence of a dynamic space-time, where quantum fluctuations or exotic physics create momentary ruptures. These ideas, while speculative, are driving new research into the fundamental nature of the cosmos, blurring the line between physics and metaphysics. As Hubble approaches the end of its mission, expected to conclude in the late 2020s, the flare has cemented its legacy. The telescope, once plagued by a flawed mirror and skepticism, has outlived its projected lifespan, delivering discoveries that continue to reshape our view of the universe. Its final years are now seen not as a slow fade, but as a triumphant encore, with the flare as its crowning achievement. Hubble's ability to capture this event against all odds is a testament to the power of human ingenuity and and the enduring value of exploration, the flare has also sparked renewed interest in preserving Hubble's data. Efforts are underway to digitize and enhance its archives, ensuring that future generations can mine them for new insights. The telescope's story is far from over. Its images, stored in servers across the globe, will continue to inspire discoveries long after it falls silent. The flare, in all its mystery, is a reminder that the universe is never fully known, that every answer leads to new questions, and that even an aging telescope can light the way forward. The cosmic flash Hubble captured is more than a scientific anomaly. It's a symbol of the universe's untamed vitality. It tells us that the cosmos is not just a place of ancient light and slow cycles, but a realm of sudden brilliant surprises. It challenges us to rethink our tools, our methods, and our assumptions, to see the sky not as a static canvas, but as a living, breathing entity. Hubble's accidental discovery has opened a new chapter in astronomy, one that promises to reveal a universe far more dynamic and unpredictable than we ever imagined. As we stand on the brink of this new era, the flare serves as a beacon, guiding us toward a deeper understanding of the cosmos. It reminds us that discovery is not a straight path, but a dance with the unknown, where serendipity and persistence intertwine. The universe, in its fleeting brilliance, has spoken, and Hubble, ever watchful, was there to listen. Now, it's up to us to keep looking, to chase the next flash, and to embrace the wonder of a cosmos that never stops surprising us.